In this week's lecture, which we're actually going to be carrying on to next week because of the amount of information that we can find in this chapter, we're going to be discussing the ways in which neurons carry information within themselves as well as communicate with other neurons to produce effective behavior. When you think about all that we're able to do, for example, like responding to pain, having hot food in our mouth, or stepping on a tack as demonstrated in this image, or grabbing onto a hot pot accidentally, we respond very, very quickly to that particular situation, lifting our foot up or retreating our hand away from the hot object. All of these things occur as a result of neurons communicating with one another. The examples that I just gave you right now involve reflexes, so it's very, very simple, a simple circuit, simple communication between neurons and fewer neurons involved. The vast majority of what we're able to do is the result of multiple different collections of neurons within the brain as well as within the body, allowing us to perform these incredible feats of behavior. So something like this is what you might see, neurons communicating within one brain region, but also sending their connections to much lengthier distances to communicate with other parts of the brain. So as we talked about before, Santiago Ramon y Cajal was the one who identified the neuron doctrine, different from the nerve net theory that Camillo Golgi had developed. When he first made these beautiful drawings that you're seeing here on the right through detailed study under the microscope using the Golgi stain, he was invited to give a lecture to discuss this theory at the English Royal Society. At this lecture was a physiologist named Charles Sherrington, and he got really, really curious. He was very interested in the neuron doctrine and got very curious about the space that existed between the two neurons. While Ramon y Cajal wasn't really interested in that, it was Sherrington who was, and who coined the term synapse, which means to clasp, and it's a term that we still use to this day. It refers to the space between neurons through which neurons communicate with one another. But there's still questions that continued following their meeting. How do neurons communicate with one another? What language did neurons speak? And what turned on or turned off a neuron? What activated or inhibited a neuron? Many of these questions were subsequently answered as technology allowed us to answer these questions, but they happened decades after the meeting of Ramon y Cajal and Charles Sherrington. So we first need to tackle the membrane of neurons. So all cells of our body are surrounded, kind of like skin, by a phospholipid membrane. This phospholipid membrane is bilayer, which means that there are two layers of it, and they're structured as diagrammed in the picture here on the right. I'm going to get my tool, my pen, so I can draw. So we have a lipid bilayer, and lipid is a fancy word for fat. We have glycerol heads and fatty tails, and because fats typically hate water, the fatty tails end up facing one another. So the inside portion of the membrane has water-loving molecules, and the outside of the membrane has water-loving molecules, but in between, smashed in between, are these lipids or hydrophobic tails. And so the extracellular space or extracellular fluid surrounds the neuron, and the inside of the neuron, which is made up of the cytoplasm or cytosol, is a watery substance as well. So you have the hydrophilic or water-loving heads facing the outside of the cell as well as the inside of the cell, whereas the hydrophobic tails are facing one another away from the watery areas of the neuron. We'll be tackling the membrane in a second because the proteins embedded within the membrane play a critical role in the ability for the neuron to generate the nerve impulse. But first I need to introduce you to a few concepts. So when a neuron isn't doing anything, it's just kind of chilling out, it is considered to be at rest. So when a cell is not generating impulses, or more technically, the action potential, it is considered to be at rest. So when a neuron's at rest, the inside of the neuron is slightly more negative compared to the outside. And by slight, I mean millivolts. So most current is measured in voltage. So you measure weight in grams or pounds. You measure current or electricity in voltage. And this difference between the inside and outside is so slight that it's measured in millivolts. And so the inside is slightly more negative compared to the outside, and this difference in charge across the membrane is known as the resting membrane potential. And we'll tackle this in a few minutes in greater depth. So how does a neuron maintain this difference in charge? And how does the electrical charge get rapidly distributed across the membrane during that nerve impulse or action potential? We'll also be tackling how the impulse is propagated or travels reliably down the axon, consistently every time, all the time, right? When you think about everything that you're able to do, that is the result of action potentials effectively traveling down your axons, permitting you to perform the functions that you do on a daily basis. Even just, listening to this lecture is the result of your neurons generating action potentials effectively down axons. All right, so what is a neuron's resting membrane potential? So I mentioned earlier, neurons maintain this electrical charge across the membrane where the inside is slightly more negative relative to the outside, and this is called the resting membrane potential of the neuron. And when I say the inside, I literally mean right against the edge of the plasma membrane. So there are these negative charges residing very close to the edge of the plasma membrane, and you have positive charges right on the outside of the cell, kind of pulling these charges to one another. There are multiple chemicals that are involved in generating this resting membrane potential. We've got the cytoplasm and extracellular fluid, so it's water and ions. And we've got the phospholipid membrane that we talked about, the phospholipid bilayer. And then we've also got proteins that are kind of wedged in between in the plasma membrane that allow these ions to pass through, as well through channels or through pumps. And again, we'll talk more about this in a second. So the extracellular space or extracellular fluid, as well as the intracellular space, are made up of water, and kind of hanging out in both of these extra and intracellular spaces are ions, which are charged particles. We've talked about the phospholipid membrane. This is an image from your textbook. It's made up of the hydrophobic lipid tails, as well as the phosphate heads that are more water-loving than the tails. All right, so ions are a fancy term for atoms that have gained or lost an electron. So most atoms are made up of protons and electrons, and when an atom loses an electron, the balance of protons to electrons is not equal, and so it takes an overall positive charge. But when an ion gains an electron, it has an overall charge that is more negative because it has an extra electron. So extra electrons, ions that have extra electrons, have an overall negative charge and are known as anions. And atoms or ions that have taken on or that have lost an electron and have an overall positive charge are known as cations. There's a rule of thumb that we'll revisit when it comes to charged particles. They are opposites attract and similar charges repel. Again, we'll revisit this rule in a second. The key ions that play a role in neurons or the resting membrane potential are sodium, denoted as Na+, because it has an overall positive charge, so it's a cation. Potassium, denoted by K, it is also a cation. Chloride, which is an anion, and calcium, which is actually a cation, but it has two extra protons that are not balanced with electrons. So calcium has lost 2 electrons to get an overall positive charge of 2. you've probably heard of proteins when you're eating things like meat or chicken, or if you're vegetarian, tofu or beans. But proteins play an integral role in our bodies. They are what DNA is used to make. And without them functioning normally, we wouldn't be able to do what we do, like on a molecular scale. So the neuron is unique because the kind of protein that exists within the membrane of the neuron allows it to do what it does. So the type and distribution of proteins is what makes a neuron a neuron. There are specific proteins known as enzymes that make or break things. There are proteins that are considered cytoskeletal proteins that we talked about last week that help give the neuron its shape. And lastly, there are proteins that serve as a pore within the plasma membrane, and these are channels. So these channels play a critical role in generating the resting membrane potential as well as the action potential that we'll talk about later. So these resting membrane potential depends on the proteins that span the lipid bilayer. And so these proteins are known as ion channels, right? So ions can't get into and out of the cell unless there's a way for them to do it. And so these ion channels serve as the pore that allow the ions from the inside to the outside or from the outside to the inside. They are made up of pieces or subunits of protein. So it's not one giant hunk of protein, but in fact they are kind of like flower petals that come together to form a pore. They're individual subunits that make up a circle or a pore. These ion channels are specific for the ions. So you have ion channels specific for potassium, and they will only let potassium through. You can't get, sodium sneaking through in those ion channels. There are two very important types of channels that exist within the neuron that help with the nerve impulse. We've got passive ion channels that always remain open under every condition. There are a few of them, but they do exist. They're passive ion channels. And we've got voltage-gated ion channels. So some ion channels are gated in the fact that certain conditions need to be met in order for them to open, otherwise they remain closed. And in this case, voltage-gated ion channels only open when there's a change in voltage across the membrane. If there's no change, the ion channel remains closed. Okay, and we'll revisit voltage-gated ion channels later on in this lecture. There are other ion channels, again, that we'll revisit in the coming lectures, but for now, for this lecture, for this week, you just need to know about passive and voltage-gated ion channels and know that they're the only really portal through which ions can pass when trying to get in or out of the cell. Another protein that's kind of important for neuronal function are ion pumps. So again, these are proteins that span the membrane as well. They're like channels, but what they do is they force ions into or out of the cell against the direction that they want to go. So they actually pump, they use up energy to push ions against the direction that they want to go. And it's an active process, so it uses the only form of energy that a cell recognizes, and that's ATP. And so as it uses up ATP, it pumps or transports ions across the membrane. One of the ones that you'll need to know for this particular lecture is the sodium-potassium pump. The calcium pump we'll discuss later on in the semester, but for now, the sodium-potassium pump alternates pumping sodium out of the cell and potassium into the cell. So for every 3 sodium ions it pumps out of the cell, it pumps 2 potassium ions into the cell, and it does so by breaking down ATP into ADP. Okay, so it's using up that energy. Okay, just to set up a little bit more of the resting membrane potential, there are 2 forces that are at play working on these ions. The first one is diffusion, and you probably know about diffusion, but haven't really, learned about diffusion as a term, but it acts on particles in any condition that are unevenly distributed in a given space. So if there's an area that has more concentrated particles, those particles are going to want to move to areas where they're lower, where there's less of them. So, physics or nature exists so that it forces particles to become evenly distributed. So if you have a condition where particles are more heavily concentrated in one area, they're going to want to go towards the area where there's less of them. And so the rule of thumb is that particles move from a higher to lower concentration. They're moving down their concentration gradient. An example of this is, putting a sugar cube in water. Over time, that concentration of sugar will dissolve, but in fact it's diffusing within that glass of water. And so just to kind of illustrate the concept of diffusion, if you've got sodium and chloride on one side of a barrier, it will stay on that side of the barrier and distribute itself within that barrier evenly. However, if given the opportunity to move, so through the insertion of these ion channels, one for sodium and one for chloride, sodium and chloride are going to move down their concentration gradients into the area where there's less of them, so then you have even distribution of sodium and chloride across this barrier, but on either side of, on either compartment. Okay, so that's the concept of diffusion. It goes from higher concentration to lower concentration. You never have lower to higher. The other force that's at play is the electrostatic pressure. So electrostatic pressure acts on charged particles. So those ions that we talked about that were either positive or negative, electrostatic pressure is going to work on them. And the rule of thumb here, as I mentioned earlier, is that opposite charges attract and like charges repel. So negative and positive are going to be attracted to each other. Two negatives are going to repel each other. Two positives are going to repel each other. So when positive charges are being attracted to negative, they're moving down their electrical gradient. And an example of, opposites attract and like charges repel are magnets. There are, two ends of the magnets, and some of these magnets, the ends kind of repel each other, whereas other ends of the magnets are attracted to each other. That's pretty much the same way in which charged particles work, except that you have pluses and minuses instead of magnetic poles. So to illustrate electrostatic pressure, again, if we have a situation where sodium and chloride are kind of dissolved in a given medium, and chloride is negative and sodium is positive, if we added a battery to create a difference in charge where one side was more negative and the other side was more positive, we would see that all of the sodiums would actually be attracted to what's called the cathode side of the battery, whereas the chloride would be attracted to the anode side of the battery, the more positive side of the battery. So these forces are acting, both diffusion and electrostatic pressure are acting on these charged particles. All right, so let's set up what's happening in the cell, and let's add in these two forces to talk about the ways in which these forces are going to encourage the movement of these ions across the membrane. So in the cytoplasm, right, this is the inside of the cell, this is the outside of the cell, and here is my handy dandy lipid bilayer. It's not drawn with two lines, but imagine that it is so. The ions that are involved are sodium, chloride, potassium, as well as proteins that have a negative charge to them. So this is how they're distributed. Sodium and chloride are much more heavily concentrated outside the cell compared to inside the cell, and potassium is more heavily concentrated inside the cell compared to outside the cell. This is not to say that you won't find potassium outside the cell. There's just much more potassium inside the cell than out. You also have a lot of these negatively charged or organic anions within the cell. So now that we know roughly where these ions are located across a plasma membrane, let's put the force of diffusion into effect. So let's look at sodium first. So sodium is more heavily concentrated outside the cell, so the force of diffusion says that it's going to want to move to where there's less of it, so it's going to want to move inside the cell. The same is true for chloride. Potassium is more heavily concentrated inside the cell, so the force of diffusion says that it's going to want to move outside the cell. All right, let's tackle the force of electrostatic pressure. As I mentioned earlier, the inside of the cell is slightly more negative compared to the outside of the cell. So because sodium is a cation, it's positive, it's going to be pulled where there are more negative charges. So the force of electrostatic pressure is going to push sodium into the cell. Not true for chloride because chloride is an anion. So it's actually going to be pulled outside of the cell. And the same goes true for potassium. Because it's a cation, it's going to actually be pulled to stay inside the cell. So we've just kind of talked about the ways in which the two forces, diffusion and electrostatic pressure, are going to work on these ions that are involved in maintaining the resting membrane potential. Okay, there's one thing that we haven't talked about, and that's what the neuron has passive ions for. So, right, I mentioned to you, ions are poor for particular ions. Passive ion channels are always open. The key here is that the neuronal membrane has channels for potassium and chloride, but not sodium. So, potassium and chloride can diffuse passively as much as they want or as little as they want, but sodium, even though you have both forces pushing it into the cell, can't go anywhere because there's no way for it to. There's no ion channel in the membrane for sodium at rest that allows it to move. It does diffuse because the forces are so great, but it does so very, very slowly. So let's look at the same exact scenario, but now with the passive ion channels included. So we have passive ion channels for potassium as well as for chloride, but remember, not for sodium. So given this, chloride will go down its concentration gradient to the area where there's less of it, and then given the fact that the inside is slightly more negative compared to the outside, some of that sodium chloride that just entered is actually going to want to go back out against its electrical gradient. What's interesting is that in the neuron, the values for electrostatic pressure and from diffusion, right, if we were to give it a number, the values for these two forces are equal for chloride. What that means is that for every chloride that's pushed into the cell, another one is pushed out as a result of electrostatic pressure. So there's what's called no net movement of chloride into or out of the cell. Right? So overall, even though chloride ions are moving into and out of the cell, because these pressures are equal for chloride, chloride is technically not really contributing to any big change in the resting membrane potential. Let's take a look at potassium channels now, right? So potassium is more concentrated inside the cell compared to out. So potassium is going to want to go down its concentration gradient to the outside of the cell. And again, so if we put in the fact that the inside is more negative compared to the outside, potassium is going to be attracted to those negative ions inside the cell and be pushed back inside. So based on its electrical gradient, potassium is going to want to stay inside the cell, but it's also going to be pushed out against its concentration gradient. So interestingly, the pressure, where's my little pointer? The pressure from the concentration gradient is actually greater for potassium pushing it out compared to the pressure for the electrostatic pressure pushing it into the cell. So overall, potassium wants to move out, right? So the pressure to move out is greater than the pressure to stay in. So it's got about a 20 millivolt difference in pressure to go out of the cell. But let's take a look at sodium, right? There's absolutely no passive ion channels for sodium, and both and diffusion are pushing sodium in. So sodium's got 120 millivolt pressure pushing it into the cell. This difference, this balance in electrostatic pressure or concentration gradient, as well as the concentrations of the ions across the membrane, contributes to the resting membrane potential. So because potassium wants to move out overall and sodium desperately wants to move in, what maintains this difference in ion distribution across the neuronal membrane? it has to do with one of the two pumps we talked about earlier, the sodium-potassium pump. Remember, for every 3 sodium it pushes out, the sodium-potassium pump pumps potassium into the cell. So what it's doing is that it's using ATP to reverse the passive movement of ions. Because sodium so desperately wants to get into the cell and potassium wants to slightly get out, the sodium-potassium pump counteracts the actions of these ions, of the forces on these ions. So for the sodium that gets in, for the sodium that gets in as a result of those two forces, this pump works to get sodium out. And for the potassium that gets out, this pump works to get potassium into the cell. So it's an active process, but it's working to reverse the passive movement of ions. And this is what helps, together with the other forces, maintains the difference in ion concentration. So this is kind of collectively the way in which ions are distributed across the membrane and maintained in their distribution. So overall, to just kind of review, chloride, there's no net movement because the pressure of both of these forces are equal. The pressures are desperately trying to get sodium into the cell. And for potassium, the overall pressure is to push it out of the cell, and this is coming largely from the concentration gradient. So collectively, the balance between the concentration gradient, electrostatic pressure, and the sodium-potassium pump contributes to what is known as the electrochemical equilibrium, and it is the resting membrane potential. In a neuron, if we were to give this a value, which is essentially the difference between the inside and outside of the cell, in a neuron, this resting membrane potential would be negative 70 millivolts. It's stored energy, which is why it's called the resting membrane potential, because it's at rest, it's at the level of the plasma membrane, and it is stored energy. That potassium wants to get out, and the sodium is desperately wanting to get in, but it's not getting a chance to do so when the neuron is at rest. So let's just summarize this lecture so far, and in the next lecture you'll get to see how the stored energy gets released in the form of the neural impulse. So information travels down the axon in the form of an electrical impulse. The electrical impulse is the result of differences of distribution of 3 ions, sodium, Na, potassium, K, and chloride, Cl, across the membrane. Sodium and chloride are more concentrated outside the cell, and potassium inside the cell. There are passive ions, these pores that are always open, passive ions for potassium and chloride, but not sodium. There are 2 forces of diffusion and electrostatic pressure acting on all of these ions. For chloride, the forces of these 2 forces are equal, but for potassium, the force is generally trying to push it out, and for sodium, they're both trying to push it in. The sodium-potassium pump works to reverse these passive actions on these ions, and at rest, the neuron has a resting membrane potential, a stored energy at the level of the membrane of about negative 70 millivolts, resulting from the balance of these 2 forces and the distribution of the ions as well as the sodium-potassium pump, which is known as the electrochemical equilibrium. So that's it for the lecture so far. Don't forget to submit your reflection.